Circuit diagrams. Drawing realistic pictures of circuits can be very difficult. So we have common symbols to represent each piece. This is what a resistor looks like in real life. That would be a pain if you had to draw that every time you wanted to do a circuit. So a resistor is drawn like this, with these little hatchy things here. A battery is drawn like this, where the longer vertical piece here is the positive side, and the shorter piece is the negative. Sometimes people will draw batteries like this. They'll put an extra two pieces in. I actually like doing it that way because then it makes it harder to confuse with a capacitor, where a capacitor is drawn as two parallel pieces. So you can almost see how that could get confused here. A wire is just a straight line. Circuit diagrams don't show where each part is physically located. It's just a logical schematic of what's going on. For your first exercise, draw a simple circuit that has a 9-volt battery with a 3 ohm resistor across the terminals of the battery, and then find the magnitude and direction of the current. Remember, we're dealing with conventional current here, which flows from the positive terminal to the negative terminal. So you can pause the video here for a second and take a shot at it, and we'll be right back with the answer. Okay, we're coming right back with the answer. And there we go. We draw a battery, 9 volts, we label it V equals 9 volts. We connect a wire up across each terminal of the battery. Right here's the plus terminal, and here's a negative. And in between we put a resistor. This resistor could be here, it could be here, it could be here. We don't care. We just need it logically to be in line with the battery. We label the resistor 3 ohms right there. And then to find the current, we use Ohm's law. I equals V over R. V is 9 volts, R is 3 ohms, and we label this with I is 3 amps. And notice the direction of the current. It's leaving the positive terminal, going up this way, then around here, like this, keeps going, and it comes back to the battery. It makes a complete circuit. We now want to add a second resistor, and there's going to be 2 ways we can do it. The first case we call series, and the second case we call parallel. Series means when I have charges, and look how I'm putting positive charges here, because conventional current is the flow of positive charges, even though we really know electrons are moving this way. If you're a positive charge, you come through, you obviously go through the first resistor, and then you don't have a choice. You have to go through the second resistor. There's no other place to go. So you go around like this and you come back to the negative terminal. So all charges must move through both resistors to get back to the battery. However, in this case, what's a charge to do? You have your charges coming like this, and you have a positive charge. It has 2 choices. It can go through there or it can go through there. Now clearly the charge is not making a conscious decision here. This is way more complex than we're illustrating. But there's 2 paths here. Some charges will go this way, some charges will go this way. But they can't go through both. They're not going to split up, right? The electrons that are coming this way can't cut themselves in half and go half each way. So in parallel, there's a choice for the circuit path for the various charges. You can go through either R1 or R2, but not both. That is parallel. Are the following sets of resistors in series or parallel? And take a minute here, and then we'll pop the answer tab out. If you need to pause the video, please do. Okay, we're back. So let's pull this out neatly here. And that's pretty good. This one is parallel. This is series. Why? There's a test you can do. Trace the shortest route around the circuit with a pen. If you find resistors on the same route, then they're in series. If they're not on the same route, then they're in parallel. Let's do the easy one first. I start here. Conventional current comes out the positive end, goes through. We hit resistor 1. We keep coming around the loop, heading back for the battery's negative terminal. We go through resistor 2, and here we are back where we started. So that's series. we find them on the same route. Now let's take this guy. We come up, we leave the positive terminal. Hey, we have a choice. Well, let's go the shortest route. We see R2, and then we have to keep going back to the negative terminal. We never did get to R1. You could take a longer route where you would start here at the terminal, go through R1, and then come back to the battery. I don't know what happened there. Like that. But we didn't hit both resistors with the same curve, so this will be parallel. Resistors and the voltage delivered by the battery determines the current. We use Ohm's law. I is equal to V over R. Circuits can be redrawn as if there were only a single resistor and a battery. By reducing the circuit this way, we can study it better. The process of reducing the resistors in a circuit to one resistor is called finding the equivalent resistance. Let's just look at Ohm's law here. We want to find the current coming out of the battery. There's only one voltage that's given by the battery. But there's two resistors, so what do? We'd love to replace these with just one resistor called R equivalent, so the current out of the battery will be the voltage over this virtual resistor that replaces the two real ones. So here we have our two resistors, and we know we have current coming out of the positive end of the terminal. What happens to the current in this circuit? We're looking for the magnitude of the current as it goes through these resistors. Remember, current is defined as the amount of charge passing a given area per unit time here. So if I have 10 charges coming out of here in a second, and they come up here, all 10 go through here in the same amount of time. All 10 are going to go through here, and they just keep pushing around in a loop like this, okay? So the current coming out of here is exactly the same as the current going through this resistor and the exact through here. If perhaps there's 10 amps coming out of here, 10 amps go through here, and you make the claim that only 8 amps go through here, what happened to all those other charges? Did they get stuck here? Did they leave? No, that's silly. Whatever goes through this resistor has to go through this resistor. So the current coming out of the battery, which we label I, equals I1, which is the current through resistor 1, and it equals I2, which is the current through resistor 2. What happens to the voltage V, which is the energy given to each charge, as it moves around the circuit? This one's a little trickier, so let's recall what voltage is. Electric potential. It's the potential energy per charge. So each charge that leaves here flowing in a current has a certain amount of energy. What a resistor does, it takes that energy of that charge, and some of the energy from the charge is transferred into heat in the resistor. It heats it up. It loses energy because the electrons here that are flowing, electrons aren't going this way. Conventional current goes this way. Electrons go this way. They're hitting the material of the resistor. They're bouncing off the atoms, the molecules, other electrons, and they're losing energy. That energy goes into the resistor, which gives it off as thermal energy. So we're losing energy. So if we lose energy, what happens to the voltage? We lose voltage. So if I come in with maybe 10 volts here, I have a 10 volt battery, after the electrons slog their way through the resistor, maybe they only have 5 volts of energy left. Again, it's not energy, it's energy per charge. Then it goes through another resistor. It loses another 5 volts, perhaps. Well, that would be the case if both resistors were the same. So at the end, your charges, your positive charges coming around this way, have no more energy. They're just getting pushed by the charges behind them. So what we have, due to conservation of energy, is the total voltage that was delivered by the battery, the amount of energy. Some of it got used up here. Used up is a bad word. Some of it got transferred to other forms of energy, and some got transferred to other forms of energy here. So the total voltage delivered by the battery equals V1 plus V2, commonly called the voltage drop across R1 and the voltage drop across R2. Let's put these concepts together to find out the equivalent resistance of the circuit, where we're going to replace multiple resistors with just one, and that one virtual resistor acts as the physical resistors. We start with the previous slide. The voltage delivered by the battery is equal to the voltage dropped across each individual resistor or circuit element. We now substitute in Ohm's law, V equals IR. So V out of the battery is the current of the battery times this R over here. This is going to be the resistance of the circuit, and actually soon we're going to find that's the equivalent resistance. I1 R1, I2 R2, I3 R3. But the current is the same everywhere in a series circuit, so I equals I1 equals I2 equals I3. In this case, we're working with 3 resistors, not the 2 that we had on the previous slides. We make the substitution for these various I1, I2, I3. Now what do you see here? I is in each term. Cancels out. We now have the equivalent resistance of a series circuit is just adding up the individual resistors. What happens if you were to add more resistors to a series circuit? What would happen to the resistance? Well, any number I add here on the right side is clearly going to make the equivalent resistance greater.